Okay, good morning, everybody. And today's lesson will be devoted to the presentation of a different method for the calculation of the electronic wave functions that is based on a different approximation with respect to the methods that I presented to you during the last lessons. Because in that case, the underlying idea was that let's say, we started from the free electron case, and as a perturbation, we applied a potential U that was periodical, and the idea was that the problem that was set with this potential was solved, making the hypothesis that we could use the wave functions or the results of the U equal to 0 case, apply a perturbation and find what happens if we switch on a potential that is different from 0 but negligible. So this was the, let's say, free electron picture with a small periodic potential. Now the idea is the opposite. So to start from the worst case, that means where the potential is strong. So we start with from the atomic picture. So the idea now is that the starting level is not the free electron level, but is the bound electron level. So the levels that you saw during the bachelor degree for what concerns, for instance, the hydrogen atom. And to apply as a perturbation the potential of the solid. So in this case, the idea is to consider this as a perturbation of the atomic picture. So before U of R different from 0 was a perturbation of U equal to 0, in this case, the potential of the solid state is considered to be a perturbation of the atomic potential. And in which, what is the picture you have to use to consider this hypothesis to be correct? If we suppose let's say, if we suppose to use this diagram where in the vertical axis we plot the value of the potential, and on the horizontal axis we plot the position. In this case, we have a periodic lattice. This is just a one-dimensional section of the problem, and if we suppose to use as a reference for the atomic potential a Coulombian term, the Coulombian term has a divergency in correspondence of the position of the ion. So in this case, what one expects about the, let's say, solid state potential is that the solid state potential goes to minus infinity at the position of the ion, and then as a maximum, and then drops again to minus infinity when the position approaches the position of the next neighbor. If you plot for comparison the, let's say, atomic potential of just one ion, the ion at the origin, in principle, the Coulomb potential has a divergency, in this case at the origin, but then goes to 0 when the position increases, the value of the position increases. So what you expect is that the Coulombian term should do something. Sorry, the sheet moved, so now it seems that there is an intersection between the atomic potential and the Coulomb potential, but actually, yeah, there's no intersection. Sorry, but I moved the sheet while making this picture. So at this point, the structure of the Coulomb potential is quite different from the structure of the solid state potential, apart from a small range close to the origin. So if one supposes to consider this small range of positions, in that situation, you may, let's say, consider that the atomic potential and the solid state potential are not so different with each other. Definitely, if you move far away from the origin, at that point, the solid state contribution is quite different from the atomic contribution. So in this picture, what is the starting point of the calculation? The starting point is the choice of the wave functions that are used to solve the problem. In this case, if we suppose that the solid state potential can be approximated or is not so different with respect to the atomic one, then we should use wave functions whose extension with respect to the origin is not so wide with respect to the range of positions where the atomic and the solid state potential are close. So the idea is to use as a starting point for the calculations atomic wave functions whose extension, whose range is small. So the idea is if the So if the extension of the wave function, and just a question, when I say extension of the wave function, what is the picture you have in mind? So what is the meaning of extension of the wave function? Yeah, so extension means the probability density is different from zero, in principle up to infinity, but let's say the position range where the probability density is significantly different from zero is of the order of the distance between the two vertical lines that I put there on the diagram. So that means that, okay, in principle, the wave function may extend up to infinity, but the range of positions where that wave function, the probability density to find an electron is significantly different from zero is reduced. So is of the order of the extension of the atomic wave functions. So in this case, the starting point is to use phi of, just to use the same index. No, let's. So the idea is to use as a starting point the atomic wave functions. So, so the starting point is the atomic problem. Due to the fact that in this case, the starting point of the calculation is not the free electron picture, but is the atomic picture. And atomic picture means that the electron is strongly bound to the ion. This approach is called tight. So this is called tight binding method to say that there is a strong binding between the electron and the ion in this case. So the idea is if we suppose that this is the Hamiltonian of the atomic picture, and let's suppose that we are able to solve that Hamiltonian. So we know the wave functions that satisfy the atomic problem. In this case, we may rewrite the so the idea is to solve the second Hamiltonian. So in case the U is not the atomic potential, but is the solid potential, just by rewriting this Hamiltonian as we sum and subtract the atomic contribution. So this is the atomic Hamiltonian, and this is the difference between the solid the contribution of the solid state, the contribution of the atomic Hamiltonian. If we call this delta U, if delta U is small, that means if the extension of the wave function that we are going to use is short, so those wave functions are not able to probe the strong difference that you have between the solid state contribution and the atomic contribution as it happens here. So here you have a strong here you have a strong difference. So the idea is to use not to use wave functions with a broad extension, but wave functions that are localized. If those are localized, then we may suppose that delta U can be considered to be a perturbation, so something small. Due to that, we may rewrite this problem as atomic Hamiltonian plus delta of the variation of the potential, and we may consider that delta to be small. So the problem will be set as a perturbation of the atomic picture. At this point, since we suppose that we have already solved the atomic situation, so we know the atomic wave functions, and just to make a comparison, atomic wave functions may mean, I don't know, for instance, the wave functions corresponding to the D levels, for instance, or P levels, depending on the solid or on the atoms you are considering at that point. So in general, are atomic orbitals that resemble, again, D, P, or S orbitals, depending on the situation you are considering. At this point, the thing that we have to tune now is the structure of the trial wave function that we use to solve this Hamiltonian. So in general, the method that is used is choose a set of functions that may be useful for the problem, make a combination of those functions to build up a trial wave function, and try to solve the Hamiltonian for that trial wave function. So the point now is what is the trial wave function that we may use to try to solve this this problem. The idea is to, again, start from the atomic wave functions, but to produce something that is a block wave function, because the idea is to solve a problem where the potential is periodical, and if the potential is periodical, then we have to use something that has the structure of a block wave function. The properties of the block wave functions are no periodicity in the direct space, because if you make a translation in the direct space, a phase appears, and in the phase you have the size of the translation. But if you go to the reciprocal space, in that case the wave function is periodical. So we need something that is periodical in the reciprocal space, and let's say quasi-periodical in the direct space, apart from the appearance of a phase. So a simple combination. So if we start from the atomic wave functions, and let's suppose, what does combination means in this case? If you suppose, for instance, that the atomic orbitals that you want to use are, for instance, d levels, then in this case, you have a combination of 5 orbitals. So the 5 orbitals corresponding to the d level, to the d levels with different coefficients. So the fact that now I write summation over m, b of m. So this combination means pick up the orbitals, pick up the wave functions of the atomic orbitals that you want to use to solve the problem and make a combination. We make a combination as we may assume that the final solution is not exactly an atomic orbital. So the simple situation is that the solution is not strictly an atomic orbitals, but can be written as a combination of atomic orbitals. So here we have a combination, but we miss two things. One thing is the wave vector, because the wave vector is an important property of the block wave function. The other thing that we miss here is the fact that this is let's say, a wave function that is fine just for one ion, because the coordinate here is r, and r is in general referred to 0. So this means that this wave function is fine just for the central ion. So first step, let's try to extend this wave function to all the ions of the lattice. And to extend that, you just rewrite this as a sum over m of b of m, phi of m, r minus capital R, where capital R is a vector belonging to the Bravais lattice, and we may make also a summation over R. So in this case, with this double summation, we have a sort of translation of the central ion wave function over all the ions of the lattice. So in this case, we have a wave function that is fine for all the ions. Now we need to include the contribution of the phase. So now we miss the phase contribution. And in this case, the phase can be included, for instance, using this method. So in this configuration, the phase that is useful for the block wave function now appears, and let's just see that in this configuration, the method that is used to introduce the phase into the system is an agreement with the fact that the final wave function is periodical in the reciprocal space. So if I make a translation like this, so if I sum a vector G, where G is a vector of the reciprocal lattice, then this is equal to sum over R of e to the I k plus G times R, and then I have the summation over M, B of M, of the atomic wave functions. And in this case, in this parenthesis, we have K plus G. So if that parenthesis is split into K times R plus G times R, then for the definition of the reciprocal lattice, e to the ig scalar product R has to be equal to 0, has to be equal to 1. So for the definition of vector belonging to the reciprocal lattice, if this is split into e to the I k times R times e to the I g R, then this is equal to 1. So at that point, we actually have the fact that if we make a translation, that translation in the reciprocal space does not change the structure of the wave function. So we have the periodicity in the space of the wave vectors. We may just check if we have the right behavior in the direct space. So we may just sum R1 vector of the Bravais lattice to the position of the in the direct space, and that is equal to the summation of the over the vectors of the Bravais lattice. Then I have the phase, and then the summation of M, P of M, Phi of M, R plus R1 minus capital R. At this point, if we just rename R1 minus R as minus R second, then this is equal to summation. So if R1 minus R is equal to minus R second, then in place of R, we should write R1 plus R second. So we may define a sort of new variable of summation, and the new variable of summation is no more R, but is R second. So this is a summation over R second. In place of R, we may use R1 plus R second. And then we have the summation of M, B of M, Phi of M, R minus R second. And in this case, the structure is equal to the structure of the starting wave function, as we have e to the, sorry, I forgot the k in the phase. So this is equal to the initial trial wave function. The only effect of the translation is the appearance of the phase in front of the wave function. So that is what we expected from the block wave function. So after making these two checks, we know that that structure for the wave function is fine for the for what concerns the with the consequences of the block theorem. So that may be considered from both points of view a block wave function. So that is fine to use for a problem that is not an atomic problem, but is a solid state problem. And the physics, let's say, from the mathematical point of view, that wave function is fine. From the physical point of view, that wave function was built up using two main points. One point is the presence of the atomic orbitals, because the problem is set as a perturbation of the atomic problem. So that's why we put there the atomic orbitals. We include the translation with the vector belonging to the direct lattice, because that wave function has to be a wave function for all the ions of the system, not just of one ion of the system. We include the phase because the presence of the phase is an important point, as if you remember, the velocity, the expectation value of the velocity operator over the block wave function is equal to, 1 divided by h bar gradient with respect to k of the energy. So if the velocity is equal to 0, that means atomic picture, because an atomic orbital, please do not consider, in this case, I suppose that velocity means capability to move within the solid. So even in the atomic picture, the electron is not at rest. So in principle, the velocity of the electron is not 0, but the capability of the electron, if that electron is described by an atomic orbital, to jump from one ion to the next is negligible. So at the end, the probability to find an electron in an ion that is not the starting ion of that electron is 0. So the translation velocity of the electron is 0 in the atomic picture. So the idea is to include the contribution of the phase within the trial wave function, because if the wave vector is not there, this gradient here will be for sure 0, because whatever the value of the energy, that energy will not depend on the k if we do not put that wave vector into the initial solution. So we need the wave vector so to have the opportunity to describe an electron whose translational velocity will be different from 0. So including that phase is important because it allows us to expect that the velocity may be different from 0. One comment, we are not imposing that the velocity has to be different from 0. We are just setting the conditions so that if that is the case, the velocity will not be 0. So we just set up the opportunity to have a non-zero velocity. At this point, so the idea is to use the Hamiltonian, the atomic Hamiltonian plus the perturbation, apply that to the trial wave function, and starting from here, the idea is it possible to, let's say, evaluate E, the energy, and find some indications concerning, for instance, the coefficients of this linear combination. So often when you have problems like this one here, you exploit one of the features of the wave functions that are used as a trial wave functions. In this case, everything starts from the atomic orbitals. If we have already solved the atomic problem, we have all the set of atomic orbitals, and the set of atomic orbitals can be produced so that the atomic orbitals are orthogonal with each other. So in general, what you do if you have a problem like this is to make a scalar product with just one of those. So the idea is to switch from the problem set in this, using this way, to phi n. So make the scalar product between the so we multiply both sides of the equation by just one of the atomic wave functions. What we try to do in this way is to reduce the number of wave functions of orbitals, let's say at the end, that you have within this calculation, due to the fact that the atomic orbitals were chosen so to be orthogonal with each other. We will have some help in this way, in this sense, but we just need to consider that the atomic orbitals are orthogonal with each other only if the atomic orbitals belong to the same ion. So as here I have set the coordinate of the central ion, because here I have no translation with a vector belonging to the Bravais lattice. This orbital will be orthogonal only to the orbitals belonging to the same ion. So if I make a scalar product with another orbital of another ion, then the result will not be in principle 0. So at this point, we may just try to solve this equation. And the idea is to exploit this orthogonal property to rewrite the psi of k as a sum of two pieces. One piece is the contribution due to the R equals 0, so the central ion, plus the summation over R different from 0 So the idea is to use the atomic wave function, sorry, the trial wave function in this way. Just a comment. I have already noticed that sometimes I miss to, as I have just done here, I miss to write the position dependence. In case I miss that, please just add the position dependence. It's not a way to say that we have not that. So here we have, sorry, this is N. Then we have the atomic, I split the parentheses, so I have the atomic contribution plus the contribution of the perturbation, and this is applied to the summation over M B of M I ask your patience here, since let's say we have just to make some calculations. Okay. Now, have you been able to copy everything? Okay, just I wait because otherwise I have to change the sheet. And there are 2 points where we may exploit the fact that the atomic wave functions are orthogonal with each other. One point is here, because in this case we have a scalar product between the orbital, let's say, corresponding to index n, and the orbital corresponding to index m, belonging to the same ion. In between, we have the atomic Hamiltonian, but the atomic orbitals are solution of the atomic Hamiltonian. So in this case, the atomic Hamiltonian disappears, and just the energy of that specific orbital takes place of the Hamiltonian. So at the end here, we are left with just atomic orbitals. Another point is here, because here we have just scalar product between one atomic orbital and a combination of atomic orbitals. So here at the end, just one of those survives. And so the only term that survives in that combination is the coefficient of that specific orbital. Okay? Yep. Okay, so So at this point, the first term where we had the scalar product with the Hamiltonian in between corresponds to B of n, because of the combination, just one coefficient survives, and that coefficient is the coefficient corresponding to the index equal to n. Then we have the energy of that level, because we had the Hamiltonian applied to atomic orbitals, but just the atomic orbital corresponding to index n survives in the scalar product. So we have just the energy due to that level, and this is everything that is left due to just the first term. Then we have the second contribution. So we have the scalar product okay, so this term is left as the atomic Hamiltonian, is the atomic Hamiltonian of the central ion, not of all the ions belonging to the system. Then there is the I just write sum over r different from 0, and I leave some dots because here this is just the same term that we have before. So it's just to save some time. I just make those points. Then on the other side, we have E of k times Bn, because on the left side, on the right side, we had the scalar product between the atomic orbital with index n and the combination of atomic orbitals. In that case, due to the orthogonality, just the coefficient corresponding to the atomic orbital with index n survives to the scalar product. And then we have E of k, and then the summation. At this point, just a comment concerning the terms that we have in this integral. This that is an integral where we have only atomic orbitals belonging to the central ion times the perturbation. So in this case, if we consider just the atomic orbitals, in principle, the atomic orbitals, if we consider the central ion, are not negligible, because the probability density corresponding to those orbitals in the central ion is the highest possible in the problem. But we have this delta U that is expected to be small, so that is expected to be the perturbation. So the contribution of that integral is expected to be small due to the presence of the perturbation. Differently, if we look at this integral here, the other integrals are integrals where in the scalar product we have one orbital belonging to the central ion and one orbital belonging to any other ion. In this case, as the extension of the atomic orbitals is quite short, we expect that all the terms where we have a summation over r different from 0 are not 0 only if the summation is over the next neighbors. So as again, from the starting point of the calculation was to use orbitals whose extension was short, then if we pick up r that is not equal to the next neighbor, but for instance to the second neighbor, at that point, the probability that the two, let's say, that the wave functions of these two ions overlap is 0 because the extension of those wave functions is very short. So due to that, we expect that here only the contribution of the next neighbors is important, because next neighbors means the fact that we may expect to have an overlap between the atomic orbital of one ion and the atomic orbital of the next ion. Due to the fact that for the next neighbors, we expect a contribution in case we have an overlap between the atomic wave functions, is the motivation behind the fact that those integrals are called overlap integrals. So this so in all these cases, the idea is that the contribution of the that the contribution to the summation is just due to the possibility to have an overlap between the orbitals belonging to next neighbors, an overlap that you do not expect to have if you consider again second neighbors, third neighbors, and so on. So in this case, the idea is that those results will be different from 0 only if we consider the next neighbors. And now, if we want to make a calculation, now in principle we should put into these integrals the exact value of the atomic orbital. But let's say using the same method that is presented in the textbook, the idea is to see what happens, just to, let's say, be able to do something more than just that when we consider a specific situation. So in place of considering the general picture where the trial wave function was the combination of many different orbitals, the idea is to consider a trial wave function that corresponds just to one orbital. And the only case where the, let's say, starting atomic orbital is just one is to consider not P, D, or F levels, but just to consider S levels. So the, let's say, just to simplify this structure, so to simplify the problem, the idea is to use just one s orbital. In this case, if we have just one s orbital, there is no combination because there is just one orbital. So the coefficient B, the B coefficients are all 0 apart from 1. So what this B of n is 1 at the end because there is just one just one orbital in the combination. So having this in mind, we have that E of n, that in this case is E of s, the E of the s orbital, minus E of k that was on the other side, is here on the right side of the parentheses. And just, and then I may take all the other terms on the other side of the equal. Then what I have is minus, I write that as psi of s Mhm. Yeah, then I have minus. And then I have plus. Yeah. Okay, as in general, let's say ES is the initial value of the energy. E of K is the value that we do not know. So I just switch the order of the two and change the sign to all the terms that are on the other side of the equal. So this is E of K minus E of S. And if you don't mind, without rewriting everything with just the change sign, I just change the signs here, plus, 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 then minus. Okay. Yeah, in this, I think I'm missing something. uh, is there a term that is not? Yeah, I forgot to. Uh, I will check that after during the break. And is there's something that is missing, but I don't know. I'm not able to find it now. Anyway, we are still able to reach the end of the calculation, because in this in the second part of the summation we have this contribution that is a constant, because a constant means that doesn't depend on K. And we have this contribution here, and this contribution that depends on K. And the point is that let's say I should not have this E of K on the other side. Okay, let's do something like this. If you don't mind, I write you the correct solution, and then during the break I check what is the problem, and then after the break I tell you where the problem was. And let's say in principle, the expression that I should have had here is the following. So E of k minus E of s So I should have had something like this. So I'm missing one term here, and then the this term and the so this should have been the final form. So this is the same of that. So always this overlap integral just with the delta U. Then here terms that involve, that is this one here, that involves the combination of the perturbation, but we have the scalar product between orbitals in position r and orbitals in position r minus r, and here when one overlap integral where just the orbitals belonging to the central ion and the orbital belonging to the next neighbor are considered. And due to the fact that if you consider this integral is the integral between the s orbital of the central ion and the s orbital of another ion belonging to the system, due to the fact that the s orbitals have spherical symmetry, the idea is that this integral should depend just on the distance, because the again the s orbital has no lobes or other structures that may include an angular dependence in this integral. So in general, this integral is called alpha of r, just to say, due to the spherical symmetry of the integrals, that should depend just on the distance. And the same is can be applied in this situation, because here we have the integral with the s orbital of the central ion times the s orbital of another ion multiplied by the perturbation. So also in this case, we expect that just the distance is important because, again, the orbitals have spherical symmetry, and in this case, the integral is told gamma. So E of k minus E of s at this point is equal to, just to simplify the structure of the equation, this integral, this one here, since that does not depend on r or on k, is just a number, that is called beta. So that is beta plus summation over r different from 0 of e to the I k r gamma of r divided by 1 plus summation over r different from 0 of e to the I k r alpha of r. This is quite often simplified in this way, that is, at the denominator there is 1 plus the summation of the overlap integrals without perturbation involving next neighbors. In general, one assumes that if the, let's say, overlap between the orbitals is small, since we have no contribution from the perturbation, that is, the perturbation is mainly located in between the orbitals. So that may favor, let's say, value of the overlap integral being different from 0. On the other side, the integral that you have at the denominator has no perturbation, just orbitals. So if the overlap is small, as you expect for orbitals that may use for the time-binding approach, then in general, one assumes that the denominator is equal to 1. So one in general neglects the summation over r that you have at the denominator. So this is in general written as beta plus summation over r different from 0 of e to the I k r gamma of r. And the important thing in this case is that if we now take, let's say, E of S to the right side, we have E of K is equal to E of S plus beta plus the summation over R different from 0, e to the I K R gamma of R. E of S is the, let's say, initial energy. Beta is the contribution of the perturbation over the central ion, but it is a number, so it's a constant, plus a summation over R different from 0 of the phase times gamma. The important thing is that we actually have the presence of the phase, because if that phase was not there, then the speed of the electron in terms of capability of the electron to translate through the solid would have been equal to 0. So no phase, no presence of the phase, or to be more precise, no presence of the wave vector means velocity equal to 0. So in this case, we expect to have the opportunity to have to observe a propagation of the electron through the system. And may I switch to another page? And so the final point yeah, so in this case, the fact that we have the opportunity to have propagation is related to gamma. If gamma is 0, no propagation. If gamma is different from 0, then we have propagation. So the velocity, that is equal to 1 divided by h gradient of the energy So if the overlap integral, including the perturbation, is different from 0, then we have propagation, because again, the term with k is different from 0. Concerning gamma, what influences the magnitude of gamma? So when is gamma expected to be large, or when is gamma expected to be small? Gamma was defined as gamma of r is equal to the overlap integral gamma of r is the overlap integral including the perturbation. So this means that if r is large, so if the ion you use for this second orbital is far away from the central ion, then this integral is expected to be, the value of that integral is expected to be negligible. C'è qualcosa che non... So that depends on the distance between the ions. So if you make a plot where on the vertical axis you plot the energy and on the horizontal axis you plot the distance, then if the distance between the ions is very large, what you expect is that the energy for instance, if you have S levels or P levels, you expect that all the possible different levels that belong to the same group are degenerate because the atomic orbit, the energy of S, P, D, F levels in the atomic picture is the same. So you have no removal of the degeneracy. But if you start to, let's say, decrease the distance between the ions, then the overlap integral starts to be different from zero. If the overlap integral starts to be different from zero, this means that if you change the value of k, then you have you're accessing different levels and the energy of those levels is different. So you start to remove the degeneracy. So the width of the band, that means the difference in energy between the lowest energy and the highest energy start to increase. And the motivation of that is, again, due to the fact that you have a k dependence in this equation and a value of gamma that decreases. If gamma increases, this means that all the possible levels that are accessed by k have energies that are more and more different with each other. And the same happens, for instance, to other atomic levels that start to overlap when you decrease the distance between the ions. If we suppose that this is the lattice spacing, then at that point the width of the band is related to the width of that, let's say, to the distance between the two lines that you have here. So between the lower line and the upper line. And let's say, is it clear for you what is the meaning of width of the band? Because to see that in a different way, we may make reference to this formula, and we may rewrite that as E of k equal to ES plus beta plus, let's just make the summation over the next neighbors, because the second neighbors probably give you a gamma equal to 0. So let's just sum up over the next neighbors. If, let's say, just suppose you are considering the next neighbor that is in front of you and the other one that is behind you. In that case, gamma is the same because the distance of those neighbors is always the same. What changes? So at the end, how can I say that? Yeah, the only thing that changes is the sign of the phase, because the one in front of you is IKR, the other behind you is minus IKR modulus, let's say. So you have that both have the same value of gamma, but two different values of the phase. I don't know how to rechange the index, but in that case, if we're supposed to have a cubic crystal, then the next neighbors have the same distance. So gamma does not depend on, let's say, gamma of R is the same for all the phases because the distance between the next neighbors is always the same. So we may also bring gamma of R out of the summation. And then we are just left with the summation over the phase. To stress the fact that gamma depends just on the modulus, I write gamma of modulus of R. And then I have the summation. If you consider this summation, the summation over the phases, if I suppose, just to make an example, that we consider just these two neighbors, the one located in place A and the other in minus A, then the value of the phase is A to the I k I. For the other one, e to the minus I k A. At this point, when you sum those two phases, the result is the cosine of ki, because you have the sum of two phases with the same argument, but just with a change of sign. So the summation gives you twice the cosine of ki. And this is the same for all the other neighbors. So you have two neighbors in the, let's say, x direction, two neighbors in the y direction, and two neighbors in the z direction. So you have a total of 3 contributions like this one here, and each of those gives you a 2 times the cosine of ki. So at the end, E of k is equal to E of s plus beta plus gamma of r, and then we have 2 times the cosine of ki times 3, because we have 3 next neighbors. So this is 6 times the cosine of ki. So at this point, if we switch to the reciprocal space, because decay dependence has to be evaluated in the reciprocal space, what is the width of the band? So in the reciprocal space, the if we are in a cubic crystal, then the center of the first Brillouin zone is, let's say, usually taken as the origin. In that case, the value of k at the center is equal to 0. So at the center of the first Brillouin zone, E of k is equal to Es plus beta plus 6 times gamma of r, since when you set k equal to 0, then the the cosine is 1. At the border, the border in general is pi divided by a. So E so if we set pi divided by a in place of k, then we have the cosine of pi. This is -1. So in this picture, the at the border of the zone, we have ES plus beta minus 6 times gamma of R. At this point, the difference in energy between the K equal to 0 value and the K equal to pi divided by A value, that is center and border of the zone, is proportional to gamma, because ES plus beta is always the same. And the difference in energy is equal to 12 times gamma, because we have plus 6 times gamma at the center, minus 6 times gamma at the border. So you have a 12 variation between center and border. So if you remember the free electron picture, the minimum energy was at the center, the maximum difference with respect to that was at the border, and then was the energy variation between the electron with the lowest energy and the electron with the highest energy. So that was a sort of width of the band. In this case, we may consider the width of the band in the same way. So difference between the energy of the, let's say, electron at the center and the energy of the electron at the border of the zone. And in this case, the difference between those two values is, let's say, apart from the factor 12, is proportional to gamma. So if gamma is equal to 0, that difference is 0. If gamma is different from 0, the difference is again proportional to gamma. So gamma influences the width of the band. That means the energy difference between all the electrons that belong to that band, or in the calculation that I have done here, that belong to the first Brillouin zone. So the idea is when you make this plot here, the plot that I showed you before, what you make in the vertical axis is the energy difference between the levels. So if gamma is 0, because the distance is so high that the overlap is 0, then gamma is 0, so you have no difference. When you decrease the distance between the ions, the overlap integral starts to be different from 0. So gamma is different from 0. And so the width of the band is also different from 0. And the closer are the ions, the larger will be the value of gamma, the larger will be the width of the band. So that's why in that diagram, you have that the distance between the two lines increases as the distance decreases. And then you stop the calculation when the distance is exactly equal to the lattice spacing of the crystal that you are considering. And yeah, the last comment, and I make the break. Due to this calculation, it appears that since the width of the band is proportional to the overlap integral, if you're supposed to be able to change continuously the relative position between the ions, then in principle, that overlap integral should, let's say, start from 0 when the distance is very large, and then continuously increase and reach a value different from 0. So what you expect is the transition between possibility for the electron to move within the solid, and the situation where this possibility, that the electron has not this possibility because the velocity is 0, is a transition that can be observed continuously, because that just depends on the distance between the ions. Actually, if you look for that and you measure that, you observe that you have no continuous transition. So at some point, when you increase the distance, the velocity of the electron drops to 0. So this is not a continuous transition, but you have at some point an abrupt change, and then the velocity drops to 0. And what is the physical motivation behind that? The tight binding approach is a sort of tunneling effect between next neighbors. So the electron tunnels from one ion to the next using, let's say, atomic levels, atomic orbitals. And thanks to this tunneling procedure, the electron is able to propagate through the system. And the probability to make a tunneling process is switched on by delta U. So the perturbation increases the probability to have this tunneling effect. But let's say, what does the electron find as it overcomes the wall, let's say, the tunneling barrier? What is found after the tunneling barrier? After the tunneling barrier, you have other electrons. So this calculation tells you what is the probability to overcome the barrier. But then as the electron has overcome the barriers, then you have other electrons. So you have the Colombian repulsion with those electrons. So it may happen that at some point, due to that repulsion, the electron is not able to jump on the other side on the barrier. So the capability of the electron to overcome the barrier at some point drops to zero. And so this is not a failure of the tie binding approach, but is a failure of the independent electron approximation, because in all the calculations, we never consider the interaction with all the other electrons. So this was just a comment to say that this continuous transition from, let's say, capability to move of the electron and impossibility for the electron to move through the solid is not observed. But this is not a problem of the tie binding method. This is a problem of the independent electron approximation, because we completely neglect the Coulombian repulsion between one electron and all the other electrons. So if you consider also that repulsion, that at some point you have no more this continuous transition, but you have a drop to zero, a sudden drop to zero of the velocity of the electrons. Okay, sorry for taking this too long, because it's more or less 1 hour and a half the time talking to you. So now, if for everybody's fine, I make the break, and then after the break, I make the comment concerning the steps of the calculation that was missing during the time binding calculation. Okay, so see you after the break.